Jnanam paramam dheyam. Knowledge is supreme.
Okay, so today I am going to use the oscillator algebra applications, whatever we learnt in oscillators, to solve problem which we have done explicitly using the position space wave function for a particle in a magnetic field, and then later on we will study angular momentum algebra using this oscillator approach. Okay, so that is the plan. If you recall, we did this in the last lecture, last week. The harmonic oscillator, we had A with A dagger as identity. This is what we will call it as an oscillator algebra, and Jx with Jy as IH cross Jz. This is what we will call it as an angular momentum algebra. So the number operator for the oscillator algebra is an eigenstate n with the number operator with eigenvalue n, and with the number operator the two ladder operators has this commutator relation, and from this we can determine A on n is square root n times n minus 1. It is a lowering operator, and similarly A dagger is a raising operator. Okay. So using this oscillator algebra, we would like to solve this problem of particle in a magnetic field, and then can we use this oscillator algebra to determine the spectrum for the angular momentum algebra. So this is the motivation for today's lecture. Okay, recall the particle in a magnetic field. Let's take the magnetic field along z direction. So this is given by this Hamiltonian, which is pi x, pi y are in terms of, it's proportional to momentum minus the shift due to the vector potential. It's pi minus EAI, and as I said already, recall the number operator eigenstate is the simultaneous eigenstate of the Hamiltonian with eigenvalue proportional to h cross omega. So in this problem, this is for a general harmonic oscillator. What this omega will correspond here, we will figure it out. So the ladder operators in any harmonic oscillator has this property, as I have already discussed for you. And in one of the earlier lecture, I explicitly went through a trial wave function and a choice of a vector potential and derived the energy spectrum to have the frequency which we will call it as a cyclotron frequency, and it's like a free particle along the z direction. So this is what we called as Landau levels. How do we obtain such an energy eigenvalues using the ladder operators which we saw in the harmonic oscillator? So a couple of things I want you to work it out is commutator of the x component with y component for pi x and pi y, and similarly we know that p with A and A with P, that order really matters. P dot A is not same as A dot P. So just to take you on how in general the potentials are functions of positions. So pi x is px minus eax, which is a function of positions. So if you take px with ax, that commutator is not 0, it will be minus ih cross del by del x of ax. This is because you know xp commutator, px with x is non-zero, and if you have any function of x, it should be del by del x of f of x. Similarly, if you try to find the px commutator with ay, you expect it to be minus ih cross del by del x of ay. So if you want to work out using these data, use these data and let's work out for a particle in a magnetic field along z direction, magnitude is b along z direction. Try to compute the pi x with pi y. The non-zero commutators are px with ay and ax with py. and that gives us a constant. Okay. So the pi x with pi y is not 0 like px and py, but this is non-zero and it is a constant, depends on the magnetic field. You can normalize the pi x by this normalization so that you can make pi x prime with pi y prime to be identity. So this is what I said in the earlier slide. Px with ay is del by del x of ay, and Ax with Py is del by del y of Ax, and if we use that here, you get curl of A, which is nothing but it's a magnetic. Similarly, the P dot A minus A dot P, Px with Ax is del by del x of Ax, P dot A minus A dot P is nothing but minus IH cross, divergence of A or del dot A. We can choose a gauge which is known to us as Coulomb gauge, where del dot A is 0, and recall that the vector potential can be changed from by a gauge transformation by a gradient of chi, but this change will not affect your magnetic field will remain same under this gauge transformation. But what happens to the Hamiltonian? Hamiltonian can in principle change to H prime. So we worked out pi x and pi y and P dot A and A dot P. Take the gauge which is the Coulomb gauge, and in this gauge pi x pi y is IH cross EB, and this is similar to our familiar XPX commutator which helped us to write A and A dagger. Okay, so that's what is the motivation. Just like we had in the harmonic oscillator x squared plus px squared, putting m, omega, everything to be 1 here, we have a pi x squared and a pi y squared, and similar to xpx commutator which is constant and non-zero, we have pi x with pi y to be non-zero and a constant. So using this, we can try to construct a new ladder operators involving pi x and pi y. So this is what we do here. We try to take the ladder operators as pi x plus I pi y with this normalization, and similarly the conjugate, Hermitian conjugate of that. And if you try to find the commutator, please check the commutator and you will be able to show that this is identity, and also construct the number operator which is B dagger B. It turns out to be, please verify this, but we need in the Hamiltonian pi x squared plus pi y squared, so you can take this term to the left hand side and try to rewrite your Hamiltonian, and the rewritten Hamiltonian is exactly similar to what you would have seen in a harmonic oscillator, with B dagger B is like the number operator, the frequency omega is EB by M, which is your familiar cyclotron frequency. So once you have this Hamiltonian rewritten looking like a harmonic oscillator, you can read off the spectrum as n plus half h cross omega c plus free particle along z direction, which is h cross squared k squared over 2m. Thing which we did, if you recall, we worked out the position space wave function. We took an ansatz trial function for it, but if you want to work it out, you have to make a gauge choice. Okay, so just for completeness, the Hamiltonian, the particle in a magnetic field Hamiltonian, suppose we take the wave function, the energy eigenvalue is E. By doing a gauge transformation A to A plus gradient of lambda, you could get a new Hamiltonian, but this Hamiltonian is what we will call it as a canonical transformation of the original Hamiltonian, because the energy spectrum remains the same. It's just that the wave function will pick up a overall phase factor, and no physics changes if you pick up the phase factors, but we will see in some situations like Born-Aronoff-Bohm effect where such phase factors will become important. If anybody is interested, can take a look at Bohm-Aronoff effect. Okay, so this is what we did in the class a couple of lectures ago, maybe, yeah, where we took a choice for A and a trial wave function, but you can also see by doing a gauge transformation using the lambda gauge parameter, you could actually get a new vector potential and try to see how the wave function changes by a phase factor. Okay, so now that we have got the energy spectrum, if you recall for this Hamiltonian, I said you should get the Lorentz force. I don't know how many of you have already worked it out, but if you have not, recall Ehrenfest's theorem, and that should be obtainable in the Heisenberg picture, writing the Heisenberg equations of motion. So in the Heisenberg picture, work out dxi by dt, which is given by your familiar commutator of xi with the Hamiltonian. So if you work it out, you will be able to see this. We would like to work out the m d squared xi by dt squared. Okay, so this is something which you need to work it out. So it's d by dt of dxi by dt. So the operator is dxi by dt, which will show up on the next right hand side with the commutator with the Hamiltonian. So this I want you to work it out. And what is your expectation? This is the force law for a particle in a magnetic field. So this should be proportional to your Lorentz force Fi. Yeah. So here this is your classical force equation where F is the Lorentz force, and let's work with the case where the electric field is 0. This is what we are doing now. We are taking a particle in a magnetic field, and this is the Hamiltonian. X component of the force, we would have written it as P cross B in classical physics, but if you go to quantum mechanics, you have to write a Hermitian operator. In fact, when you write the Heisenberg's equation of motion for d squared xi by dt squared, you will exactly get this combination B cross B minus B cross V will show up there. Okay, please check it. So please check that this force, the quantum mechanical force form for the Lorentz force, should have the Hermitian operator, which is the combination of dr by dt cross B minus B cross dr by dt for the Lorentz force. And we can set E to be 0 because we are working with electric field set to 0. Okay, so far I have tried to show how using the harmonic oscillator algebra, trying to write the Hamiltonian for a particle in a magnetic field in terms of the ladder operators, we could get the spectrum, and I've also tried to use the Heisenberg's equations of motion and derive for you the familiar Lorentz force. We will move on to the angular momentum algebra, taking some of these data of these ladder operators and whether we can find the states for the angular momentum operators. So recall the orbital angular momentum and the spin angular momentum, which we discussed last week for the Stern-Gerlach experiment. So Lx Ly is IH cross Lz, and L dot L commutes with all the components. For conventions, we are going to take it with respect to Lz, and we write it to be a simultaneous eigenstate of Lz and L dot L, and these are the eigenvalue equations with eigenvalues which we have seen when we discussed this hydrogen atom. And the questions we should ask is how Lx operates on Lm, and similarly how Ly operates on Lm. Okay, what do we get are the questions which you would like to know. So we have seen orbital angular momentum and spin angular momentum. They obey the same algebra. This is what I tried to motivate you from the Stern-Gerlach experiment. It exactly behaves, the algebra of the spin operator should be exactly similar to what we have. Plus, they are in two different spaces, they have to be 0. And we have this condition, which is the simultaneous eigenstate of L squared and L Z. We checking the I to be the Z component for convenience and universally following whatever books are doing. And similarly, you can have it to be a simultaneous eigenstates of S squared and SZ. Instead of trying to talk whether we are talking about orbital angular momentum or spin angular momentum, we will compactly write angular momentum by a symbol J, and the J will satisfy the same property, and we will write eigenstates of J squared and Jz to be the simultaneous eigenstates. So we have done this ladder operators. The ladder operators are not Hermitian operators. You cannot experimentally observe them. A is not equal to A dagger. That's why you have two ladder operators. They are not Hermitian. Similarly, we would like to do a ladder operator here using these angular momentum Jx, Jy and Jz. Okay. So motivated by this harmonic oscillator ladder operators, let's write J plus as J1 plus IJ2. I'm using 1, 2 and 3 as X, Y and Z. Okay. And J minus as J1 minus IJ2. It is similar to the angular momentum operators, which I am writing J plus and J minus, are looking similar to the way we wrote non-Hermitian operators in the oscillator algebra. What is the next thing? I had this Jx, Jy to be IH cross Jz. I would like to write the commutator of J plus with J minus, J plus with Jz and J minus with Jz, so that I can try to play around and find how to go about this problem. So write down the algebra using these ladder operators, which is J plus or minus with J3. What will this be? Can you work it out? What is this? The negative sign, right? Correct. What is this answer turning out to be? So it's twice H bar J3 and do the J plus with J3. Excellent. So it is minus plus H cross J plus or minus H cross. So the same algebra of Jx, Jy, Jz which we wrote, I am trying to rewrite. Yeah, J plus with J minus what it is, which is like your A and A dagger. Something wrong? Minus. Okay. Both of them are minus? Yeah, sorry. The third one is plus, the second one is minus. Okay, I'll correct it. Please try to. So J plus with J3 or Jz is minus H cross J plus, and J minus with Jz is plus H cross J minus, and J plus with J minus is twice H cross Jz. Now let's compare with the harmonic oscillator. Kind of said that the states are eigenstates of Jz from the hydrogen atom experience, right? So this is similar to your number operator, roughly, not exactly, okay? It's like Jz operator is like number operator. If I write my state as Jm with Jz operator, it gives you Mh cross Jm. We have one more because we know J dot J. It's an eigenstate of J dot J. That is why I put this additional index. Otherwise, I could have just worked with M. Okay. The maximal compatible set for an angular momentum algebra is simultaneous eigenstate of j dot j and jz. That's why I have two integers. So jz is like your number operator in harmonic oscillator. It's an eigenstate with eigenvalue mh cross. Then what does it tell us? J plus and J minus are like your, I don't know, one of them will be A and the other one will be probably A dagger, or the other way around. Okay. So this algebra will actually tell you what happens to J plus on Jm. If you remember, when we did the oscillator, we tried to say that A on n, how did we argue A on n? A on n went to, I don't know whether this is m minus 1 or m plus 1. So I think it is like A dagger and this is like A. Rewrite it that way, then this will become a plus sign, that will become a minus sign. Then that will be like the A dagger and A. Excellent. This has to make you think also and do it. So use this algebra and try to figure out that it is like a ladder operator. It's not an eigenstate, but this one will be an eigenstate, right? This will be an eigenstate of Jz with eigenvalue m plus 1 h cross. That's why we wrote the state as. Use this algebra. Similarly, the next one to figure out that it will be a lowering operator. You see the power of algebra now. How we are exploiting the power of algebra. What is left? You have to determine these coefficients. That's right. So that is from the hydrogen atom data, but we will do it independently now and show that how the restrictions are. That's right. So those things will come to. Those things are not visible here. I'm just saying it's like, if it is exactly harmonic oscillator, there's nothing more to do. As he is pointing it out, there is no information that m goes from minus j to plus j, and you can't have raising operator going to infinity like the way you did it in harmonic oscillator. Okay, so we need to fix those things. We'll come to fixing that. I'm just saying that you can, if Jm is an eigenstate given to you, which is a simultaneous eigenstate of j squared and jz, I can actually get the trend how the j plus and j minus operates on it from this algebra. That is all I said. But this coefficient of proportionality has to be fixed, and also these issues that m should go from minus j to plus j. Also j could be integers or half odd integers. All these things are not fixed right now. I'm just using hydrogen atom data. I am just doing this. But we will now do explicitly to figure out all these informations. So I need to figure out that j and m goes from minus j plus 1 till plus j. This has to be figured out. You have to also figure out whether j could be 0, half, 1, 3 by 2, These are the possibilities as we do. In the orbital angular momentum in hydrogen atom, it was only integers. Now we have to naturally see whether we can get half odd integers. This is also to be figured out. What else? I need to also figure out Jm as some dm on Jm. What is this dm? J minus on Jm is some Cm on J. Sorry, this is m plus 1, m minus 1. I need to figure this out also. Some of these things have not been fixed as of now. So we need to fix this. Is this clear? The problem clear? How do we do this? Yeah. So there is another nice trick which we are going to do. This is what is the Schwinger method. Let's do that just as a. Okay, so this is things I've said except for this negative sign which is here. So all the other things are fine. And we can write simultaneous eigenstates Jm, which is an eigenstate of j squared, and J3, and we will show that J plus is a raising operator and J minus is a lowering operator. This also you can see from this algebra is what I was trying to tell you. Only proportionality constant has to be figured out using this above algebra. Not only that, as he has already pointed out, that we need to figure out m takes values from minus j to plus j. We have to also figure out that j could be integers, could be half-odd integers, all these possibilities, because if you do Stern-Gerlach, j is actually half. If you do orbital angular momentum, j is actually integers. So all possibilities are allowed, has to be figured out. We have not still done that. Okay. So for that, we use the Schwinger oscillator method. What is the theme? Theme is to generate the angular momentum algebra using two independent oscillator algebras. There are two independent oscillators for the system, one with A and A dagger, another one with B and B dagger. Don't confuse this B with what I wrote with pi x plus. So this is just two independent oscillators. You can call A1 dagger, A2 dagger if you want, but you can as two independent oscillators. So we are going to write a dress. This is what is called representation. Right? You can represent the angular momentum ladder operators j plus j minus and jz or j3 as follows. Let's take two ladder operators with one of them as raising and another one as lowering. By independent I mean that between A and B the commutator is always 0. A and A dagger is harmonic oscillator algebra, B with B dagger is harmonic oscillator algebra. Between A and B or A and B dagger or A dagger and B, A dagger and B, A dagger with B dagger, they are all 0. This is what I mean by rest of the commutators are 0. They don't talk to each other, they are independent. Using two independent harmonic oscillator, we could write a product of two ladder operators. If you note here, one ladder operator is like raising, the other one is like lowering. It is this combination which we take. The j minus is Hermitian conjugate of this. You can take the dagger of this and you should get the j minus. Order really doesn't matter because whether I put first B and next A or A and B doesn't matter because they commute. I can work with this. So now to find what is j3, substitute these two here and determine what you get for j3. I'll leave it to you to do this. Please try this out. j3 should be a function of again involving the four ladder operators. Okay, please try this out. And interestingly, if you work this out, you will find that you get it to be a difference between the number of operators. Please work this out. Okay. Similarly, work out what is j dot j. Please work out what is j dot j. Na is the number operator for the harmonic oscillator with ladder operators A and A dagger. So Na is nothing but it's A dagger A. Nb is the harmonic oscillator with ladder operators B and B dagger. I am not bothered about the frequencies of the two oscillators. For me, I am more interested in constructing the angular momentum algebra in terms of the two harmonic oscillator ladder operators. Is it okay? So please work this out j dot j and tell me what you get. Okay, please verify whether you get this. Let me stop here today.